What's up, everybody? Welcome to lecture 27. Today's lecture is all over section 5.4 and 5.5. And to start off with, we're going to talk about work. Now, in algebra-based physics, some of y'all may remember, or may have taken that class in the past, and you may remember from it, that work is equal to the product of force times distance. But this is assuming that force is constant. So what if force isn't constant? What if, for example, it's something like this, where force increases with some linear distance? So to give you an example of what I'm talking about, let's say I apply some initial force to this chair as I'm moving it along, and I start increasing that force. Not exactly the best example because I wasn't really accelerating too much there, but it gives you an idea of what I'm talking about. So force being non-constant throws a monkey wrench into this. It makes us run into this problem where it has this problem now associated with it where that's not work anymore. Force, non-constant force times the distance just doesn't really mean anything. So when force isn't constant, what's work then? Well, to think about that, you got this example on the board where force increases exponentially as a function of position along some line. Looking at this, it may not be obvious what to do right away, but one thing we could do, so I could approximate this function with a bunch of small functions that are piecewise continuous. So what does that look like? What does that all mean? Well, that means I could approximate that with another function that looks something like this. Right? So it accelerates through. Now, if I do that, I could take and find, or rather form, a bunch of rectangles and find the area underneath these rectangles and add all of those up. Because after all, that would be force, right? That would be the force, the height of that rectangle, times the width, the distance traveled through that rectangle. In other words, we could do this. And we could go one step further and let these rectangles get as small as we want. We could get an arbitrarily close approximation by making those rectangles, those approximations, for arbitrarily small chunks of time. But hey, isn't that just this? Isn't that all that is? Yeah, that's it. That's all. So, in other words, for the case where force isn't constant, work, once I get this all erased, work is equal to the definite integral of force with position. That's it. That's all there is to it. And we're going to look at one quick example And I'm going to go with the easier example because it spells out what this is doing fairly well. But having said that, I absolutely want y'all to go look at the notes and look at the example of water being pumped out of a cone. It is more in depth and it gives you a lot more to chew on. It gives you a better picture of what's happening. So I want y'all to look at that example on your own, but in the lecture videos, we're going to go through the easier spring constant example. Cool, so let's get to it. All right, so for this first example, what we've got is a spring being hung from the bottom of let's say a shelf. That the bottom of the spring reaches down 1 meter below the shelf. Now, we're going to add a weight of 11 newtons to the bottom of the spring. And when we do, we get that this spring stretches down 5 meters. How are we going to use that information to figure out the work done on the spring? Or rather, the work done by the spring? Well, to answer that question, we need to talk about this idea from physics known as Hooke's law. Hooke's law tells us that the force applied by a spring is equal to some constant times the displacement of the spring. So if you stretch the spring, that amount of displacement, or if you compress the spring, that amount of displacement. Well, in our case, the displacement here is obviously equal to 4, right? We don't know what K is, but we know that the work done, that the force done has to be equal to 11 newtons. So this lets us then solve for K. K is equal to 11 over 4. So the force done by this spring is going to be 11 over 4 times the displacement of the spring. Now, how are we going to use this to find work? Well, coming over to our formula for work, we're going to set up this integral. Obviously, f of x is this 11 over 4x. We're integrating with respect to x. Now, what are our a and our b? You might be tempted to say, well, obviously a is equal to 1 and b is equal to 5. Seems like the obvious choice, right? It does seem like the obvious choice, but it would be wrong. And the reason why it's wrong is this is measuring displacement, not initial distance to final distance, but the displacement itself. So, we're thinking of the initial position as 0. If 1 meter below, though, is 0, then 5 meter below is 4. And this sets up our problem to solve. Now we just integrate it like we normally would, right? This is going to come out to be 11 over 8 times x squared, evaluated from 0 to 4. Well, this then is going to come out to be 11 over 8 times 16, or we can say, what is that? 22 Newton meters. And that's it. That's all there is to this problem. So remember, work is measuring displacement. So we need to assume that initial position to be 0. Because you're not talking about work done before you started pushing it. You're talking about work done from where you started pushing it to where you ended, right? or in this case, from where you initially were when you added the mass to where you finally got to after you added the mass. So this is a distinction that needs to be made and needs to be understood and clear. Having said that, let's check out one more example of these work problems, and then we're going to get into the average of a function over some sort of range of x values. So let's check that out. All right, now in the second example, we've got a particle that's just moving through space. And this particle is moving with a force of x squared plus 2x as measured from the origin. Now, what we want to answer is how much work is done by the particle as it moves from x equal to 1 to x equal to 3. Well, unlike the previous case, we're now measuring our force with respect to distance from the origin. We're no longer measuring it from its initial resting position to where it goes. Now we're saying the force is a function of distance from the origin. As a result, to set up this integral, what we're going to have is the integral from 1 to 3 of x squared plus 2x integrated with respect to x. And the reason, again, for this difference is what's actually being measured as distance, right? In this case, this is distance from the origin. In the previous case, it was the distance of displacement. So in the case of the spring, we're talking about how much we moved it, right? Whereas in the case of this particle, we're talking about a force that's no longer based on how much you move it, but where it is compared to the origin. And for that reason, these integrals get set up a little bit different. So, setting up this integral to find the work done by this particle would be as such. That's really all I have to say about work. I just wanted to show you all these two examples because the distinction, the importance here, the emphasis needs to be made on the fact that the bounds of your integration depends on what you're measuring your force to be a function of. Is it of displacement from a resting location, or is it from the origin? And that does change the integral just a little bit. And it is some minutia here, but it's important. So for example, in that last problem, had we set it up with that 1 and that 5, we would have gotten a totally different answer. A different answer that would have been wrong. It would have been 25 minus 1, so 24 times 11 over 8, and that would have given us the wrong answer entirely. So, it does matter. What you are measuring this force with respect to matters, and it tells you how to set up the bounds of this integral. So be aware of that. Know that when you're going into these problems. It's a really common mistake to make. It's a really easy one to make. Oftentimes, I think of this as being the easiest part of the semester, of the class, but this is also the area where some of the most common mistakes occur. I mean, these are the problems that everyone's going to make the same exact mistake. And it's going to be because of understanding what you're measuring your force with respect to. That's the trick here. The integral is easy enough to set up. The problem is knowing what you're measuring your force with respect to. So keep that in mind. Be aware of that. Having said that, now we're going to move on to averages of functions. So the average value of a function. over some domain of x. I think we're going to do one more example after we talk about this average value of functions, and that'll be it. See you all in a second. Now, to talk about averages of functions over some domain, I thought it'd be best to start by just considering what we know about the average value of a thing, right? So let's say we have a bunch of y values. We want to know what the average of those y values are. Well, then we just add them up and divide by the number of y values we have, right? That's what that is up there, right? Where f evaluated at x sub I, that's your y value, that's y sub I. So you're just adding them up and then you're dividing by the number of y values you have. Well, let's assume that x, all of our x values are evenly spaced. Then, if that's the case, this tells us that n is equal to your last x value minus your first x value divided by the distance between your x values, right? That's all that is. So, just as a plug of information, A is equal to x1, and B is equal to xn. So just some details. So if this is the case, then we can rewrite this formula. We can rewrite it as 1 over b minus a, all divided by delta x, times the sum of f of x sub I from I equal to 1 up to n. Well, that thing we could rewrite. We could flip all this around and make the math a little bit easier for us. So doing that really quickly, that's going to give us delta x over b minus a times the sum from I equal to 1 up to I equal to n of f of x sub I. Well, hey, delta x is a constant, so why don't we bring that into the series? Because we can. When we do that, we get this expression. The series from I equal to 1 up to n of f of x sub I times delta x, that quantity, times 1 over the difference between b and a. You know what? That looks like something, doesn't it? It looks like the sort of thing that if I were to attach the limit as n goes to infinity to, I might get an integral out of it. That is what the average of a function is over some domain. What? That's ugly. So let's put it in integral notation. Putting it in to our lovely integral notation, we have b minus 1 over b minus a times the integral from a to b of f of x integrated with respect to x. In the end, that's the average of a function. This tells us the average value of your function over that domain of x. So over those x values from a to b. And that's pretty nifty. That's really actually convenient. Because think about how many things in life we talk about in terms of averages. If you're a physicist or a engineer, you're going to have to take calc-based physics. And when you do, you're going to be talking about moments of inertia. Moments of inertia, you need to talk about the center of mass. The center of mass needs to talk about the average distribution of this continuous quantity. It needs to talk about the location of that distribution. The average location of that distribution is what I should say. That's what it is. That's what the moment of inertia is calculating for. It's calculating for, well, I shouldn't say that's what it's calculating for. It's calculating for the moment of inertia. This is giving you the center of mass, which you need. That's actually really handy. That's really cool, really nifty. Because it tells us a lot of different things about, say, this cool example problem, which we're not actually going to solve in this class because it gets into math above this class, but it is a problem that requires this idea. Let's say somebody were to dig a hole through the center of the earth. And let's say somebody rolled a ball into that hole. How far would that ball go? Would it get stuck in the center? No, it falls all the way through, and then all the way back up, and then all the way through, and it keeps going like that. Of course, there's energy loss to heat and blah, 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 blah. This thing gets really hot, it falls apart, and you don't have a perpetual motion machine here. But you do have a really cool example that uses this formula, this integral, this average value of a function. So having said that, let's check out the rest of the material because there's some cool implications from this idea. All right, so the last thing I want to talk to y'all about is this integral form of the mean value theorem. And what the integral form of the mean value theorem says is just that if you have a function that's continuous on some interval from a to b, then there is a c value between a and b such that f evaluated at c is equal to the average value of your function. Now, another way of saying that is that the integral of your function from a to b is equal to b minus a times f at c. So there's these two different ways of saying that. Now, just to see an example of how we might use this average value of a function, we've got this problem down here at the end. We want to find the average value of the function 1 plus x squared on the interval from x equal to -1 to x equal to 2. Well, this thing is just going to be 1 over 2 minus 1, 2 minus -1, my mistake, times the integral from -1 to 2 of 1 plus x squared, integrated with respect to x. Well, this is going to give us 1 over 3 times the integral of 1 is just x. The integral of x squared is 1/3 x to the third This is all being evaluated from -1 to 2. And from here, it's just algebra, right? So I'm going to leave the algebra to y'all. That's all this is. There's not much more to this than that. Having said that, I think that's all I have for y'all today. If y'all have any questions, as always, please come to office hours. I've really only had one person show up to any extent. So if y'all are having problems getting into office hours, let us know, let me know, especially since it's over Zoom, and it's not just over Zoom, it's linked to Zoom through Blackboard, and we've had some problems this summer with different tech programs and tech devices not working the way they should. So if you've tried to show up to office hours and I haven't been there or something along those lines, maybe it's not letting you into office hours, let me know so we can fix that. Like I said though, I think that covers everything for today. So if y'all have questions, shoot me an email, stop by office hours. Yeah, have a good one, everybody. Okay, so I just realized today is Monday and I totally forgot about today's office hours. So I apologize about that one, guys. That one's on me. But otherwise, to excluding today, if y'all have tried to go to office hours and I haven't seen me there, let me know, because that means there's a problem with Zoom and the way Blackboard's set up and everything else. Yeah. Anyhow, have a good one, everybody.